Learning objectives. In this chapter, the user would learn the following in detail: numerical differentiation, maximum and minimum values of tabulated function, numerical integration, trapezoidal rule, Simpson's rule for numerical integration. Numerical differentiation. Numerical differentiation is the process of finding the numerical value of a derivative of a given function at a given point. In general, a numerical differentiation is more difficult than numerical integration. The area of the trapezoids shaded approximately equals the area bounded y is equal to f of x. Integral a to b f of x dx equal to delta x by 2 inside the closed bracket f of x naught plus 2 times of f of x1 plus 2 times of f of x2 plus f of x3. This is because while numerical integration requires only good continuity properties of the function being integrated, numerical differentiation requires more complicated properties such as Lipschitz classes. Numerical differentiation is implemented as ND stands for numerical differentiation inside the closed bracket f, x, x0 scale tends to scale. In the mathematical package numerical calculus. Numerical integration. There are many applications where derivatives need to be computed numerically. F dash of x approximately equal to limit h tends to 0 f of x plus h minus f of x divided by h. The simplest approach simply uses the definition of the derivative for some small numerical value of h less than 1. Now we are going to see like a table with 3 columns. First column has derivative at x0 and then second column error, third column difference type. We are going to see the table row by row. First row, dy by dx equal to y1 minus y0 by h, and then error is order of h, difference type is forward. Second row, dy by dx equal to y0 minus y minus 1 divided by h, error is order of h, difference type is backward. Dy by dx equal to y1 minus y minus 1 divided by 2h, error is order of h square, difference type is central. D square by dx square equal to y2 minus 2y1 plus y0 by h square, error is order of h, difference type is forward. Next row, d square by dx square equal to y0 minus 2y minus 1 plus y minus 2 divided by h square, error is order of h, difference is backward. Next row, d square by dx square equal to y1 minus 2y0 plus y minus 1 divided by h square, error is order of h square, difference is central. Next row, d cube y by dx cube equal to y3 minus 3y2 plus 3y1 minus y0 divided by h cube, error is order of h, difference is forward. Next row, d cube y by dx cube equal to y0 minus 3y minus 1 plus 3y minus 2 minus y minus 3 divided by h cube. Error is order of h, difference is backward. Next row, d cube y by dx cube equal to y2 minus 2y1 plus 2y minus 1 minus y minus 2 divided by 2h cube. Error is order of h square, difference is central. Maximum and minimum values of tabulated function. Find the minimum or maximum value of f of x equal to minus 3x square plus 2x minus 4. Then state the domain and range of the function. Step 1. Determine whether the function has minimum or maximum value because a is negative. The graph opens downward and has a maximum value. Step 2. Find the x value of the vertex. X equal to minus b divided by 2a equal to minus 2 divided by 2 into minus 3 equal to 1 by 3. Substitute 2 for b and minus 3 for a. Find the minimum or maximum value of f of x equal to minus 3x square plus 2x minus 4. Then state the domain and range of the function. Step 3. Then find the y value of the vertex. F of minus b by 2a into f of 1 by 3 equal to minus 3 times of 1 by 3 whole square plus 2 times of 1 by 3 minus 4 equal to we getting minus 11 by 3. The maximum value is minus 11 by 3. The domain is all real numbers or the range is all real numbers less than or equal to minus 11 by 3 or y such that y less than or equal to minus 11 by 3. Numerical integration. Numerical integration is the approximate computation of an integral using numerical techniques. The numerical computation of an integral is sometimes called quadrature. Uses the word quadrature to mean numerical computation of a univariate integral and cubature to mean numerical computation of a multiple integral. There are a wide range of methods available for numerical integration. A good source for such techniques is Preset al. 1992. Numerical integration is implemented. Mathematica as numerical integrate in the closed bracket f x x minimum x maximum. The most straightforward numerical integration technique uses the Newton-Cotes formulas, also called quadrature formulas, which approximate a function tabulated at a sequence of regularly spaced intervals by various degree polynomials. If the endpoints are tabulated, then the 2 and 3 point formulas are called the trapezoidal rule and Simpson's rule respectively. Closed interval a comma b, open interval a comma b, off closed interval a comma b, off closed interval a comma b. The 5-point formula is called Boole's rule. A generalization of the trapezoidal rule is Romberg integration, which can yield accurate results for many fewer function evaluations. We have shown some useful intervals for numerical integration in the table. Table has 3 columns. First column w of x, second column as interval, third column xi are roots of. We are going to read the table row by row. First row 1 minus 1 comma 1 pn of x e power minus t 0 comma infinity ln of x e power minus t square minus infinity comma infinity hn of x 1 minus t square whole power minus 1 by 2 minus 1 comma 1 tn of x 1 minus t square whole power 1 by 2 minus 1 comma 1 un of x power 1 by 2 0 comma 1 x power minus 1 by 2 p2n minus 1 square root of x power minus 1 by 2 0 comma 1 p2n square root of x. If the functions are known analytically instead of being tabulated at equally spaced intervals, the best numerical method of numerical integration is called Gaussian quadrature. By picking the abscisses at which to evaluate the function, Gaussian quadrature produces the most accurate approximations possible. However, given the speed of modern computers, the additional complication of the Gaussian quadrature formalism often makes it less desirable than simply brute force calculating twice as many points on a regular grid, which also permits the already computed values of the function to be reused. Modern numerical integrations methods based on information theory have been developed to simulate information systems such as computer-controlled systems, communication systems, and control systems, since in these cases the classical methods which are based on approximation theory are not efficient. Smith 1974. Simpson's rule and trapezoidal rule, numerical integration. Integrals do not have to get very complicated before symbolic methods fail to work. Consider, for example, the integral 0 to 1 cos of x cube plus x into dx. There are no symbolic methods based on indefinite integration that can be brought to bear on this problem. Instead, we can sample the integrand at regular integrals and carry out an estimate based on this. One way of doing that is to approximate the function by a sequence of straight line segments as in the figure. The area between each segment and the x-axis is a trapezium, meaning that if the width of the interval is h and the y values at each end of the interval are yi and yi plus 1, then the area of the trapezium is 2 divided by h inside the bracket yi plus yi plus 1. The entire area between the curve and the x-axis, which is to say the integral, can be approximated by adding together several such trapezia. If there are n trapezia and n plus 1 y values ordinates running from y0 to yn, then the integral is approximately Tn is equal to 2 divided by h inside the bracket y0 plus 2y2 etc. At the end there is a yn. This is called the trapezium rule. An alternative, which is often, though not always, more accurate, is to approximate the curve with a sequence of quadratic parabolic segments instead of straight lines. Each parabola requires 3 points to specify it, so each parabola spans 2 intervals. This method can only be used, therefore, if the number of intervals is even and the number of ordinates, therefore, odd. Now, consider the quadratic passing through the points minus h, y0, 0, y1 and h, y2. It's not hard to show that this has the equation y equal to y0 minus 2y1 plus y2 divided by 2h square into x square plus y2 minus y0 divided by 2h into x plus y1. If we integrate this between minus h and h, we get 3 divided by h into y0 plus 4y1 plus y2. This would also have been the area if we would situated the middle of the interval somewhere other than 0, though the calculations would have been harder. So from our quadratic approximation, we get the estimate Sn is equal to h by 3 inside the bracket y0 plus 4y2 etc. at the end yn, where n must be even. This is Simpson's rule, is shown in the table. S4 equal to 0.25 divided by 3 into 0.58395 plus 4 into 1.35335 plus 2 into 0.81096 equal to 0.6349. Conclusion. In this chapter, we have covered the following in detail: numerical differentiation, maximum and minimum values of tabulated function, numerical integration, trapezoidal rule, Simpson's rule for numerical integration.